Mastering algorithms, a journey from foundations to expertise in the ever-evolving world of computer science. Mastering algorithms is essential for anyone aiming to excel in software development, data analysis, or competitive programming. Whether you're preparing for technical interviews or simply looking to deepen your understanding of problem-solving techniques, algorithm tutorials serve as invaluable resources. The path to algorithm mastery begins with a solid foundation in core principles. This guide explores how structured learning, practice, and application can transform your approach to tackling complex computational problems efficiently. Fundamental concepts every learner should know before diving into advanced algorithms. It's crucial to grasp foundational concepts such as time complexity, space complexity, and basic data structures. These elements form the backbone of efficient algorithm design and implementation. Understanding Big O notation allows programmers to evaluate how an algorithm's performance scales with input size. It helps distinguish between linear time solutions, O, n, and exponential time approaches, O, 2 to the power of n, guiding developers toward optimal choices. Data structures like arrays, linked lists, stacks, queues, trees, and graphs play pivotal roles in implementing algorithms. Selecting the right structure often determines the feasibility of solving a particular problem efficiently. Time complexity measures execution time relative to input size, helping identify bottlenecks in code. Space complexity evaluates memory usage, which becomes critical when handling large datasets or constrained environments. Mastery of these fundamentals enables learners to analyze existing algorithms critically and devise new ones that address specific challenges effectively. Bridging theory and practice through hands-on learning. Theoretical knowledge alone isn't sufficient. Applying concepts through coding exercises reinforces understanding. Engaging with interactive platforms offers immersive experiences that blend theory with real-world scenarios. Platforms like LeetCode, HackerRank, and Codeforces provide curated problem sets categorized by difficulty level. Solving these problems systematically builds confidence while exposing users to diverse algorithmic patterns frequently encountered in industry settings. Example: implementing binary search on sorted arrays teaches both divide-and-conquer strategy and edge case management simultaneously. Such exercises cultivate analytical skills required for debugging complex systems later in career journeys. Coding challenges designed for skill development. Structured coding challenges follow progressive difficulty curves designed specifically for skill enhancement. They begin with simple tasks like finding duplicates in unsorted lists before advancing towards intricate graph traversals. Evaluating solutions based on runtime efficiency encourages optimization mindset. Comparing brute force methods against optimized versions highlights trade-offs inherent in different implementations. Exploring core algorithm categories. Algorithms fall into distinct categories based on their purpose and methodology. Familiarity with these groups aids in recognizing suitable approaches during problem-solving sessions. Sorting algorithms, techniques like quicksort, merge sort, heap sort, insertion sort, selection sort, and bubble sort organize data in ascending/descending order. Their efficacy varies depending on dataset characteristics. Searching algorithms, binary search operates on sorted collections using logarithmic time complexity, whereas linear search examines elements sequentially with linear time complexity. Graph traversal, depth-first search, DFS, and breadth-first search, BFS, explore nodes systematically, applicable in shortest path calculations and connectivity checks across networks. Dijkstra's algorithm finds shortest paths in weighted graphs, commonly applied in routing protocols and map navigation services. Kruskal's and Prim's algorithms construct minimum spanning trees useful for network design and clustering applications. Each category presents unique advantages and limitations, requiring careful consideration when selecting appropriate methods for given situations. Advanced topics requiring deeper dive. Once comfortable with foundational areas, exploring advanced subjects broadens horizons significantly. Dynamic programming, greedy algorithms, backtracking, and randomized algorithms represent higher-level paradigms worth investigating thoroughly. Dynamic programming optimizes recursive solutions via memoization techniques, storing intermediate results to avoid redundant computations. Classic examples include Fibonacci sequence calculation and knapsack problem resolution. Greedy algorithms make locally optimal decisions hoping for globally optimal outcomes. Applications range from Huffman encoding compression schemes to activity selection scheduling problems. Backtracking systematically searches solution spaces by building candidates incrementally and abandoning partial solutions upon encountering contradictions. Used extensively in constraint satisfaction puzzles like Sudoku solvers. Randomized algorithms incorporate randomness for improved average case performance despite potential worst-case degradation. Monte Carlo simulations and Las Vegas algorithms exemplify this approach. Case studies demonstrating practical impacts examining real-world implementations illustrates how theoretical constructs translate into tangible benefits. Consider Google Maps route-finding capabilities powered by modified Dijkstra's algorithm variants enhanced with heuristic estimations. Netflix employs recommendation engines leveraging collaborative filtering combined with matrix factorization techniques derived from eigenvalue decomposition principles, an elegant fusion of linear algebra and machine learning concepts. Blockchain technology relies heavily on cryptographic hashing functions, SHA-256, alongside consensus mechanisms like proof-of-work/POS involving probabilistic verification processes akin to randomized algorithms. Navigating common pitfalls during learning process. Many beginners struggle with grasping abstract mathematical representations behind algorithms. Overcoming this hurdle demands consistent effort coupled with targeted remediation strategies. One frequent mistake involves misinterpreting asymptotic notations. Remembering that constants matter less than growth rates simplifies comparisons between O, n log n, versus O, n superscript 2, complexities for larger inputs. Debugging faulty logic remains another challenge area. Utilizing print statements strategically along with unit tests helps isolate errors early during development phases rather than waiting until deployment stages. Overlooking edge cases. Always test boundary conditions explicitly since unexpected behavior often manifests there. Ignoring time constraints. Prioritize algorithms meeting specified runtime requirements unless alternative constraints justify exceptions. Developing habits around systematic testing ensures robustness across varying input sizes and types, a vital competency sought after in professional circles. Leveraging resources effectively across different stages. A wealth of educational materials exists catering to varied learning styles and proficiency levels. Choosing appropriate resources aligned with personal goals accelerates progress substantially. Books. Classics like Introduction to Algorithms by Corman et al., Algorithms Illuminated series by Tim Roughgarden offer rigorous treatments ideal for self-study enthusiasts seeking deep dives. Online courses. Platforms such as Coursera host courses from prestigious universities covering algorithm design principles comprehensively. Specializations combining theory with hands-on projects enhance employability prospects notably. Videos/tutorials. YouTube channels dedicated exclusively to algorithm education break down complicated topics visually appealingly. Visual learners particularly benefit from animated walkthroughs demonstrating algorithm behaviors dynamically. Communities. Participating actively in forums like Stack Overflow or Reddit's r/learn programming exposes individuals to peer reviews, fosters collaborative spirit, and keeps them updated regarding emerging trends regularly. Crafting personalized study plans based on goals. Creating customized study schedules tailors efforts precisely according to individual aspirations, whether focusing solely on interview preparation or pursuing academic research avenues. If targeting technical interviews, prioritize mastering commonly asked questions from top tech companies. Allocate significant portions of study plans towards practicing whiteboard interviews simulating actual scenario pressures authentically. For researchers aiming publications, delve deeper into specialized fields such as approximation algorithms, online algorithms, or distributed computing models relevant to current scholarly pursuits. Regardless of chosen path, incorporating regular revision cycles prevents forgetting previously learned material. Spaced repetition systems prove highly effective in reinforcing retention over extended periods. Building confidence through competitive programming. Participating in contests sharpens problem-solving acumen dramatically. Competitions force participants to think creatively under press. Focus initially on easy medium-rated problems available on contest platforms. Gradually increase difficulty once comfort zones expand adequately enough to handle harder challenges confidently. Analyzing others' solutions post-contest reveals alternative perspectives potentially overlooked earlier. Studying high-rated submissions enhances appreciation for elegance and efficiency achievable within tight deadlines. Joining virtual teams collaboratively working through challenging problems strengthens teamwork abilities alongside domain expertise, both crucial soft skills demanded across industries nowadays. Real-world applications beyond textbooks. While textbooks lay groundwork, practical applications demonstrate true power of algorithms shaping modern society profoundly. Understanding these contexts enriches comprehension vastly beyond mere syntax memorization. Search engines. PageRank algorithm revolutionized information retrieval by assigning importance scores to web pages based on link structures, forming massive directed graphs globally. Social networks. Recommendation filters utilized by Facebook/Instagram rely heavily on graph algorithms identifying connections likely beneficial for user engagement metrics measured continuously. Healthcare. Medical imaging technologies leverage image processing algorithms detecting anomalies invisible to human eyes swiftly, aiding diagnoses accurately and promptly saving countless lives annually. Finance. High-frequency trading operations depend critically on sophisticated quantitative models employing stochastic calculus alongside statistical arbitrage strategies executed millisecond-wise. Continuous improvement strategies for long-term growth. Maintaining momentum requires adopting sustainable practices fostering lifelong learning attitudes instead of treating algorithm studies merely as temporary milestones. Active recall. Regular quizzing oneself on fundamental concepts improves recall effectiveness compared passive reading alone. Flashcards containing key formulas and definitions facilitate rapid review sessions conveniently. Pomodoro technique. Breaking study sessions into focused intervals interspersed with brief rests maintains concentration quality throughout prolonged periods, enhancing productivity overall. Mind mapping. Creating visual diagrams linking related algorithm themes organizes thoughts coherently, enabling better assimilation of interconnected ideas seamlessly. Teaching others. Explaining difficult topics aloud forces clarity upon oneself, naturally refining conceptual understandings further. Tutoring peers reciprocally benefits both parties, mutually strengthening foundations together. Conclusion. This exploration has outlined numerous facets, comprising successful algorithm tutorial engagements, from establishing strong bases through gradual advancement towards specialization domains richly rewarding personally, professionally. To truly harness algorithmic prowess, commit yourself fully, embracing continuous improvement ethos wholeheartedly. With dedication, persistence, and strategic resource utilization, unlocking full potential lies firmly within reach, awaiting determination to pursue relentlessly forward.